Welcome back. We were talking about amplitude modulation as part of the communication systems discussion. So we know that we need to send signals through channels, and as of such, we need to modulate them. And of course, when we get them back, we need to demodulate them. So one of the most common way we modulate in this particular, we are basically changing where the center of frequency is for our signal is through this amplitude modulation. And so what happens is that we have our signal, the signal that we really are interested in passing on through air or through whatever mean. We'll use air as an example here. Then what we'll do is we'll use a carrier frequency, carrier signal. This is the signal that would determine where the center of frequency is. Instead of being zero, is going to move it someplace else. What is usually referred to as CT. In here, we're gonna use two signals. We're gonna use the J omega CT, which is basically an exponential function, but it just gives you a one-sided carrier. This is a one-sided carrier. If you want a two-sided carrier, so we have a positive and negative frequencies, we will probably use, we will use cosine of omega CT as our carrier for that function. Remembering, before we go too far, remembering this really is e to the j omega CT plus e to the minus j omega CT. And the only change is the magnitude is divided by 2 using Euler's. I'm not just applying Euler's to this relationship. So this one gives you positive and negative, that gives me just the positive side. But as far as how we handle this, it's going to be very similar for both cases. Before I go too far, first, and then talking about the output is just a multiplication of the two functions. And so if this frequency centers at 0 radian per second, this would be centered at omega c radian per second, omega c being the carrier frequency we have chosen. Now, why do we want to do this? Here's why we want to do this. If voice, for example, is going to be from 0 to 20 kilohertz, it's going to be very low. It's going to be through the black area, which, if you recall, this is the high impedance area, so nothing is going to make through for very far. Most of it's going to be consumed with the impedance of the air. So I really would like to be here, even though my signal is sitting in here. My carrier frequency allows me to move it here, so I'm in the low Z. This would be the low impedance area. So that's why we do a carrier. We send it through the air on the receiving end, they grab it and bring it back to here, so we can listen to it on our speaker or whatever it is that we are dealing with. Okay. All right. So that's what it is. And let me kind of show you in a time domain what the signal looks like. So this is my information bearing signal. So this is basically the x of t that I'm getting. This x of t comes in, and the carrier comes in, and the carrier gets multiplied by that, and what comes out of it and goes through the air is this. As you notice, the envelope, this dashed line on the outside is called envelope, represent this carrier, but the frequency, the actual signal frequency, would be the carrier frequency, and that's what y of t is. This is on the sending side or the modulation side. This on the receiving end, you will receive y of t, and you literally do the same thing. You go over here, this gets multiplied, and then what you get back, and then you filter stuff, and just so you don't get any of the aliases, and what you get back is a time domain. So this would be your transmitter or sender transmitter, and this would be your receiving end, what comes to you, and then you decipher it. What you get back is the original signal. So this process is called, this side of it is called modulation. This side is called demodulation, and we send, this is what travels through the air, or through the channel, whatever your channel is. And here I use the air. And this omega c is called the carrier frequency, and this is your information bearing, or well, let's call it signal. They usually call it information bearing signal. Okay, so that's kind of what we're doing. What we're going to do the rest, this is the essence of this. Now you know amplitude modulation. What we're going to do in the next few minutes that we have together in this video is we're going to see what is the math behind this that make this thing possible. Okay, and we're going to start with a carrier. We're going to start with a simpler case. So we're going to start with when the carrier is where the carrier signal is e to the j omega c t. So if that is the signal we have, then therefore, based on what we've been doing, what's going to go through the air, the y of t that comes out of our modulator is basically going to be x of t times e to the j omega c t. Now, since if you look at the Fourier transform properties of this thing and try to use the Fourier transform, you'll find that the y of j omega is equal to basically shifted. We don't even have to do much work with this one. It's basically going to be whatever the original x was shifted by the carrier frequency. Just go to the table, look it up. You can derive it if you want. So, but the important part to realize is what exactly is happening. So we know what's happening in time domain because we just talked about it. Now let's take a look at it. Look at it and see what happens in the frequency domain. In the frequency domain, what we've got our signal, Fourier transform of signal x of j omega. It's going to look like, by the way, when they draw this triangle or TP, all they're saying is there's a signal from with a frequency maximum of omega m going through there, but I don't know what it is. I don't care what it is. I just know the maximum is there, centered around 0. That's my signal. For example, voice would be 0 to 20 kilohertz. 2 pi times 20 kilohertz would be its omega m. All right. So if I take this and remember what c e to the j omega was. C to e to j omega basically said at omega c, the carrier c, omega c, it's got a value of 1. And this is your c, your carrier, Fourier transform of your carrier frequency. So now if I convolute these things, move one around and convolute it with each one, because that's what's going to happen. If it's a multiplication in time domain, it would be a convolution. Or you can just simply look at this and say, oh, okay, this y of j omega, the result is going to look like, it's going to be basically omega m plus omega. Actually, a better way to say this thing, so let me erase this one. Better way to say this. The center of this, instead of being at 0, now it's going to be at omega c, and this interval here and this interval here would be omega m. So basically what we are saying, let's take a look at the time domain version of this. What basically we're saying, our signal in x of j omega was just a signal at that frequency, low frequency, then got multiplied by the omega cosine of t and has a really high frequency, but the envelope still looks just like x of t. So that's more or less. And since this is x of j omega, we just have that upper envelope. We don't have the bottom envelope. So if you want the bottom envelopes, you want to have the lower portion there too. It's called a two-sided. What we just did was a one-sided. So if you wanted to do two-sided, all we have to do is say, okay, instead of having our carrier, just simply be a sine, e to the j omega, what we're going to do, we're going to use a different color. Now, instead of having a carrier be e to the j omega, we're going to say our carrier is cosine of omega c t. Okay, and also we realize that this omega c t is basically e to the j omega plus e to the minus j omega. So, and also if you just look at so if we let the, of course, the x of t is the original signal we have, and let's say x of j omega is its Fourier transform, and that's a Fourier transform of it, and then we have the Fourier transform of this one. the Fourier transform of j omega is going to be pi delta omega minus omega carrier plus delta omega plus omega c carrier. So if you do the multiplication, which would be a convolution of the other side, what you'll end up with is y of j omega is going to be equal to 1/2 of x of j omega minus omega c plus x of j times omega plus omega c. So what that picture looks like, again, once again, if we assume our signal is omega m0 omega m minus here, let's say this is 1, then my carrier, as we talked, my carrier is two-sided because its cosine has the positive side and the negative side. So my carrier, so this was x of j omega, my signal bearing, then my carrier j omega would basically be a impulse. Hopefully the impulse would be way out there. So let's do it properly. So to make sure, because if it's that's the other thing to really think about, is that the C in general, you want your omega carrier to be much larger than maximum frequency, otherwise you're going to have aliasing because the ends will overlap each other. But so let's say omega c sits here, the carrier sits here, the value of the carrier would be pi in this case, and you're going to have 1 over here. So this is going to be minus omega c, this is going to be omega c, and really there is nothing here, nothing. This just was the axis I drew. Okay, so now if I so this would be my c of j omega. So if I go ahead and convolute these things, what I'm going to end up with is y of j omega, okay, which is basically going to be one picture here, one picture here, and so pretty much what's going to happen here is just going to be 1/2. The size is just going to go down to 1/2. This is going to be centered in omega c again. This distance is going to be the maximum frequency of that, and similar thing is going to happen in minus omega c. Now the beauty is, if I run it one more time through this, which I just mentioned it briefly in the last case we had for demodulations, if I run it back through the process again, as I was showing here, what's going to happen is that when I run it through, this will move, this 2 will move this way, omega c, and that way back, and the original signal will get back out if you put a filter through it, okay? There has to be a need for a low-pass filter here to clean the signal back out, okay? So that's basically a modulation, demodulation. The goal is to take a frequency and move it in frequency spectrum to where it's going to go through. For example, for an AM station, a human voice is being transmitted, music and things like that. That's 20 kilohertz. So what they do, they take that 0 to 20 kilohertz, and they put a carrier frequency somewhere between 0.5 megahertz to 2 megahertz. Clearly, that carrier frequency for that case would be, let's say 1 megahertz in the middle of the range, is much larger than omega m, which is 20 kilo. We're doing F version, but you can multiply by 2 pi times 1 megahertz. It's clearly much larger than 20 kilohertz times 2 pi. So that's kind of a quick summary of modulation, demodulation. And again, once again, I want to emphasize that at least for the cosine version of this, you can just basically take the carrier, if you want to recover your signal, multiply it, and there comes your original signal back out. Okay, you may have to have a low pass filter to clean up all the extra stuff that is in there. that gets us to the end of the AM or amplitude modulation. One of the techniques of getting the signal to where it would go through the best part of the spectrum from a low impedance point of view. So that means it can go farther, lose less energy per miles, and all that kind of good stuff.